Hello and welcome to my presentation about advanced crack detection in liquid and gas pipelines. My name is ALFRED KUHN. I'm the CEO of the European entity of LINSCAN. I want to start my presentation with a safety moment, because safety is paramount for all that we do, and especially in the current situation of the pandemic, which is still raging on. So I want to remind you that you need to wear your masks properly, meaning they need to cover mouth and nose, avoid handshakes, practice social distancing, and practice good hygiene. Overall, don't let your guards down. Thank you very much for your attention to my safety moment. The agenda, I will go a little bit into basics. What is a crack? Why pipelines crack? Refer to stress corrosion cracking in more detail, and then I will introduce to you the options we have to detect cracks reliably. At the end, a brief summary of the presentation, some conclusions, and when we are ready for the discussion. First of all, we need to understand what is a crack, because this is an important part of the whole discussion about crack detection. And I'm referring here to the specifications as provided by the Pipeline Operators Forum, and which can be read in the version of 2016. A crack is a planar two-dimensional anomaly feature with a high length to width ratio, a sharp root radius, and a possible displacement, which means a surface opening of less than 0.1 millimeter of the fractured surface. A crack-like feature has a similar definition. However, the surface opening is between 0.1 and 1 millimeter. So this is the difference between crack and crack-like features. How does this look like in reality? You can see here schematic of a pipe wall and a crack, which is a disturbance in the metal grid, which does not necessarily have an opening. Whereas a crack-like feature has a distinct opening, and as it is written in the definition of 0.1 up to 1 millimeter. In reality, you can see here that this is what would be called a crack, and here this is a crack-like feature. This is important to remember, and I will come back to this a little bit later in my presentation. Why do pipelines crack? Pipelines crack because over time they deteriorate, and this deterioration or degradation increases over time. I've shown you here 4 examples of cracks which mostly occur across the globe, and this is fatigue cracking, hydrogen-induced cracking, sulfide stress cracking, and stress corrosion cracking. If you look at the abbreviations for C and D, this should not be mixed up. SSC is not to be mixed up with SCC. The first part we need to understand is, how does it come to cracking? And except for the fatigue cracking, which is that the material with repeated stress fatigues, gets brittle and breaks, the other types of cracking all require that there is a surface film breakdown. And the surface film breakdown means that there is a liquid between the coating of the pipe and the pipe wall. And this is where small pits start, and depending on the type of exposure of the pipeline to stress and the composure of the liquid which is in that area where the barrier has cracked, it develops either into metal loss features or into cracks. Metal loss features are areas with distinctive metal loss whereas cracks are characterized by a very, very small amount of metal loss, but a very big threat to the integrity of the pipeline. The characteristic of a crack is also that cracks grow over a certain period of time with a very, very small rate. But all of a sudden, and this is the danger of cracks, this rate increases dramatically and leads to unexpected failures. So the prediction of when cracks get dangerous is very, very difficult, and there is no reliable method developed so far which can determine when a crack will reach that exponential growth rate. This means that it is important to detect cracks early. The most dangerous and most occurring crack type is stress corrosion cracking, which goes back into the 1960s when the first types of this cracking were detected in the US, and which was later categorized as high pH stress corrosion cracking. The other type of stress corrosion cracking is near neutral pH, and this was first identified in Canada in 1985. What all these stress corrosion crack types have in common is that they appear in pipelines with high temperature, with high pressure, and also with alternating pressure. And this is not alternating 1 or 2 bars, this is high differences in pressure, 10, 20, 30 bar difference. And with many fluctuations of this pressure. We talk here about pressure cycling. Another characteristic is that this type of cracks appears very often in the first 15 to 20 kilometers after a compressor station or after a pump station. Now, how can we detect cracks? There are 2 technologies which are used for crack detection. In liquid lines, it's ultrasonic crack detection, or UTCD. And in gas pipelines, the electromagnetic acoustic transducer technology, also called EMAT. The difference between crack and crack-like features we have discussed already. Now, this is important to understand because this also gives us the explanation why tools based on the magnetic principle like MFL or TFI cannot detect cracks. They can detect crack-like features, but not cracks. And the reason is that in a crack, the magnetic field just passes along without being deflected. Whereas a crack-like feature deflects the magnetic field, and the sensors of the MFL or the TFI tool get a reading. So it is possible that the magnetic tools see crack-like features, but not cracks. This is an overview of feature detection capabilities. And the message here is that several tools exist for feature detection in pipelines, but there is no tool which can see it all. If we go back to the crack detection tools, I want to start with the oldest of these crack detection technologies, which is the ultrasonic crack detection, which is used in liquid pipelines. And the principle is that an ultrasound is generated, travels to the pipe wall, and is reflected on the inner pipe wall and the outer pipe wall. And by the time which the ultrasound needs to travel back to the transducer, we can determine the distances. Now, if we look at the principle of wall thickness measurement, we see that the sensor is in a 90-degree angle to the pipe wall. And this means that if we have cracks in a pipeline, our ultrasound, because it is in a 90-degree angle, will not see these cracks. So the data analyst later on, when he sees the data from the tool, he will see nothing in the data. So this is why the crack detection tool was developed. And the principle here is that the sensor is not at a 90-degree angle to the pipe wall, but at a 17-degree angle, which means that the ultrasound beam, when it is entering into the pipe wall, is traveling in a 45-degree angle, and that cracks in the pipe wall will reflect a part of the ultrasound, which can be read by the transducer. This happens from both sides, so that we get a reading from the left side or from the clockwise side or the right side, which is also called the counterclockwise side of the crack detection tool. So every crack will be seen from several sensors and from both sides. And by this arrangement of sensors around the circumference, we achieve a high probability of detection and a high probability of identification and sizing of crack features. The tools which exist on the market generally can all see longitudinal cracks. There are certain companies who also offer the detection and identification of circumferential cracks. The report that you receive after a crack detection inspection is the same format as you know it from metal loss inspections, the feature list with all the features which have been found with by dimensions, locations. You get also the distribution plots along the pipeline. The difference is that compared to a metal loss inspection severity assessment, which is giving you an estimated repair factor, the crack detection assessment gives you an anomaly assessment factor, and the repair curve looks different. These are some examples of real cracks which have been found in real pipelines, longitudinal cracks, and also axial cracks. The other tool which is used for crack detection is the EMAT. And this tool was especially developed for the use in gas pipelines. Because in gas pipelines, the standard UTCD tool cannot be used because there is no liquid couplant. And no gas pipeline operator wants to have a liquid couplant in his pipelines, because this requires afterwards cleaning, drying, which is cost intensive. So the EMAT tool was developed, and you can see the difference between the two methodologies. The UTCD tool needs the liquid couplant to transport the ultrasound from the transducer into the pipe wall. The EMAT tool uses also an ultrasound. However, the ultrasound is created inside the pipe wall. The picture shows the difference between the standard UTCD tool and the EMAT tool. The ultrasonic crack detection tool uses a liquid couplant to transport the ultrasound, which is created in the transducer, into the pipe wall. The EMAT tool, however, creates the ultrasound inside the pipe wall. The picture shows the two different methodologies that the tools use. The ultrasound crack detection tool uses a transducer, and the ultrasound is transported from the transducer through the liquid couplant into the pipe wall. The EMAT tool, however, creates the ultrasound inside the pipe wall by a fluctuating magnetic field with a high frequency, which makes the metal grid swing and creates the ultrasound inside the pipe wall. This is how the EMAS tool looks like. It is a little bit similar to the magnetic flux leakage tool, which you may know. And this is because it uses a static magnetic field and also a fluctuating magnetic field to create the ultrasound inside the pipe wall. The benefit is that you do not need a liquid couplant. And an additional benefit is that this tool may also see coating disbondment. Here you see the two principles of creating the ultrasound in the pipe wall. One is using Lorentz force, the other is using magnetostriction, where my company has opted for the magnetostriction method, which gives certain advantages over the Lorentz force method. The biggest advantage is that the sensors do not need to be that close to the pipe wall as with the Lorentz force method, and that we get a better level to noise ratio for the reflections which come from the features inside the pipe wall. Here are some findings of the EMAS tool. We have a crack field, we have a gouge, and we have here an area of coating disbondment. The coating disbondment is determined by a difference in amplitudes, because where we have the coating attached to the pipe wall, the resulting amplitude is lower than from an area where we have no coating directly at the pipe wall. And if we have an area of approximately 60 square centimeters, then we can determine that this is an area of coating disbondment. It must be said that this must be a full area where the coating is disbonded from the pipe wall. To come to the end, efficient crack detection is available for liquid lines and for gas lines. In liquids, it is the ultrasonic crack detection tool. In gas, it is the EMAS tool. Both methods have a high accuracy in detecting and sizing cracks and also crack-like features. One recommendation at the end: every crack detection inspection should be accompanied with an inspection for metal loss. The reason is that some metal loss features may have a sharp edge, and this sharp edge may be interpreted as a crack. So by the combination of the crack detection and the metal loss inspection, the data analyst has it much easier to determine what kind of feature he is looking at. So therefore, the recommendation to have a metal loss inspection accompanying every crack detection inspection. Thank you very much for your attention, and now I'm ready to take your questions.